In this screencast, we're going to answer the question as to what you do when you cannot recall the gas constant R or easily look it up in a table, but you still want to use the ideal gas law to do some kind of calculation. One way to do this is to convert from standard conditions. And what I mean by that is, say you're using the ideal gas law to figure out the volume of gas X at some certain pressure and temperature, but you can't recall the gas constant R. If we rewrite this using standard conditions, and I'll define those in a second, we'll write PS and some molar volume Vs, and that's going to be equal to the gas constant R and a standard temperature. If we divide that first equation by the second equation, we are left with something of the form that looks like this. And what this allows us to do is we know that for any ideal gas, given a pressure of 1 atmosphere and a temperature of 0 degrees Celsius, we'll call these standard conditions, it's going to have a molar volume of 22.4 liters per mole. Now this might also be written as 22.4 meters cubed per kilomole. And of course, depending on the units, there are other numbers that could be memorized. These numbers might be a lot easier to memorize than, say, a gas constant with the appropriate units. So given this information and a memory of, say, 22.4 liters per mole, we can then use these numbers at any time without ever having to use the gas constant R. Let's provide an example of this. Let's take a look at an example where we're flowing propane gas into, say, a grill, and pardon my horrible drawings. Let's say that gas is at 45 degrees Celsius, 2 atmosphere, and we know that we are flowing it at a mass flow rate of 2.2 kilograms per hour. What we want to know is the volumetric flow rate. And the first place to start is to determine the molar flow rate so that we have all the variables necessary for our ideal gas law. In this case, the molecular weight of propane is 44 grams per mole, or 44 kilograms per kilomole. Since we're working with kilograms an hour, we could go ahead and convert that to kilograms per kilomole. Taking the mass flow rate and dividing by the molecular weight gives us 0.05 kilomoles per hour. So now in this case, we can't look up the gas constant R, but if you recall from above, we know that P over PS, V over V bar S equals NT over TS. And we could rearrange this so that we could solve for our volumetric flow rate. And so when we do this, it should look like the following. And we can start putting in our variables. We have 0.05 kilomoles per hour. That's going to be times the temperature, 273 plus 45 degrees Celsius, is going to give us 318 Kelvin over the standard temperature, which is 273 Kelvin. Multiply this by our standard pressure of 1 atmosphere over the pressure we're interested in at 2 atmosphere, and that number that we can memorize a little easier, 22.4 meters cubed standard temperature and pressure per kilomole. When we do this calculation, we get a V bar that's equal to 0.652 meters cubed per hour. If those units are good enough, we could stop there, or we could convert this to liters, which would give us 652 liters per hour. So hopefully you could see that we never needed the gas constant R because we used the standard conditions.